All right, let's move on to our next talk. This is Alex Fleming. Just a brief history of Alex's life. Alex is married to Laura, and they've been members here for about 2 years. He has a bachelor's degree in music education and a bachelor's degree in physics from both from Texas A&M University Commerce. He also has a master's degree in theoretical nuclear astrophysics from Texas A&M College Station. Alex has worked, I find this fascinating, in between his degrees he's worked as a truck driver, which is quite commendable. Between the two bachelor's degrees, he has worked as a researcher at the Texas A&M Cyclotron Institute, worked at NASA, and currently works at Lockheed Martin in Fort Worth. It's my pleasure to introduce Alex Fleming on The Dust from Which We Came, involving the constants in the universe. So if you would welcome Alex.
Hello. Thank you. As he just said, I'm Alex Fleming. So I've had a bit of a winding road to get to where I am today. If you were here for my last lecture that I gave, you may know that I started out in college as a music major. But eventually I found my way back to school to study physics, and my last lecture was, unsurprisingly, over the physics of music. But for this lecture, I'm going to be diving more into the subject I studied in graduate school, which was nuclear astrophysics. I know that may sound a little daunting, but please don't worry. I'll be speaking qualitatively about a lot of the stuff, so I did a lot of math for this presentation, but that doesn't mean you have to. Ultimately, the math is supposed to tell a story, and I'm hoping that I can do that just as well. So if I've done my job right, you should hopefully come away with at least a better understanding of how finely tuned everything is, and have a better appreciation for the miracle that we're here to ponder creation itself. So there we go. So, as much as I would love to take credit for this animation, I didn't make it. This is a hydrodynamical simulation of the formation of a star from protostellar nebula that is made by Matthew Bates using 3 million particles running a simulation in a supercomputer. This is a top-down view, so we're looking down on the protostar from what would be its north pole. And also, for the question that you had earlier about like how do we know a lot of this stuff, many such simulations that we do, we will use simulations like this in order to confirm ideas that we might have. So we basically start with some general ideas of how nature works. We program those things into a supercomputer and we let it run. Yeah. Okay.
So you might want to start over.
You want me to start over?
Yes, our apologies.
That's okay. So this is a simulation from Matthew Bates using 3 million particles and running a simulation in a supercomputer. So at the very beginning, all the dust and gas is evenly distributed, and the particles all have random velocities. As the simulation proceeds onward, you'll start to see a rise in the density and temperature towards the middle. So like right here, this is actually not the surface of a star. This is the dust and gas that has been collapsing, and it starts getting dense enough that it starts pushing back on the stuff that is falling into it. Whenever we move past this point, at some point the particles start bouncing around and will start to tend to start spinning. This is because the initial cloud had some total angular momentum, and as the particles bounce off of each other, the velocities they had in opposite directions tend to cancel out. But they tend to keep their velocities going in the same direction. And as the cloud shrinks, the angular momentum is conserved. So the object in the center will begin to spin faster and faster, like an ice skater that's pulling their arms in. This causes a spherical cloud that is like spherical in all directions to tend to collapse into a rotating disk. And this is also why our solar system is mostly planar, and mostly all of the objects are rotating in the same direction. At some point, the cloud of dust and gas is collapsed into from some huge radius, like a light year across, to something a bit more like twice the distance to Neptune. it has started spinning to conserve its angular momentum, and the heavier elements tend to find their way to the center as the protostar starts to form. I refer to this as a protostar because in order to be considered a star, there needs to be some sort of nuclear fusion happening. As friction between the particles causes them to fall into the center, the density and temperature and pressure in the center start to skyrocket. And once the temperature reaches about 1,000,000 degrees, the very first nuclear fusion can begin and a new star has officially been born. So before we go about the nuclear process, oh, actually, hold on. Before I get too far down this rabbit hole, I want to take a moment to have a disclaimer. So I need to acknowledge for what for some people will be a point of contention. This morning's talk is about stellar nucleosynthesis, the creation of chemical elements inside of the hearts of stars. The nuclear process presupposes a universe which is about 13.8 billion years old, where generations of massive stars needed to have been born, lived, and died to seed the cosmos with elements that would make up our world. I'm aware that there are a great many deeply faithful Christians out there who believe in a young earth, and I want to say very clearly that this lecture is not meant to be a criticism of those who hold that belief. My task here isn't to settle debates within the church, nor do I feel qualified to have that conversation. I've just been asked to talk about our current understanding of astrophysics, what it says about how stars work, and through that lens, I'm hoping to show you a glimpse as to what a miracle it is for us to be sitting here this morning to talk about it. C.S. Lewis once wrote, suppose Hamlet wanted to meet Shakespeare. He couldn't climb into the attic to look for him. The only way that Hamlet could know Shakespeare is if Shakespeare wrote himself into that play. In the same way, the only reason we can know anything about God is because he has written himself into our story. That's the perspective I'd like you to keep in mind going forward. Regardless of what your view is, we're still talking about how God wrote himself into the story for us to better know him. Psalm 19:1 says, the heavens declare the glory of God, and the skies proclaim the work of his hands. And it is precisely this work, his creation, that we're going to be talking about together. So let me proceed onward with where I was. Okay, so before we get into the nuclear processes, I need to talk to you about the pieces of the elemental puzzles. Here are the actors of the nuclear reactions. At the top we have our nucleons. These are particles that feel all four forces of the universe: the strong nuclear force, the weak nuclear force, the electromagnetic force, and the gravitational force. On the left we have the proton, and on the right we have the neutron. I'll get into more specifics later, but for now, know that these are the particles that make up the nuclei of atoms. In the middle, we have the leptons, and in this case, the right side is the familiar electron, and the left side is the positron, the positively charged antiparticle mirror image of the electron. And in the third row, we have the energy carriers. Photons will be represented by this wave packet, and neutrinos are going to be represented by this little tiny dot here. They are very tiny particles that are really hard to detect, and they'll be represented by that. So first, I'd like to talk about beta decay, because this will be important to a lot of things later. So the neutron is slightly more massive than the proton. It has a mass of about 939.6 mega electron volts, as opposed to the proton's 938.3. This means that it's not in its ground state, and if left alone, it will decay into a proton. The typical half-life for bare neutron is about 15 minutes before it spontaneously decays into a proton, an electron, and an antineutrino. The neutrino is a very light, ghost-like particle that is only part of the reaction to make all of the equations of conservation of momentum, spin, charge, and everything else balance appropriately. It also carries a very tiny bit of energy out of the system in the form of its mass and momentum. It doesn't hardly interact with anything at all, so basically once it's created, it books it for the exterior of the star and sets off into the unknown. Electrons carry the opposite charge of a proton, so 0 becomes +1 and -1 for the proton and the electron. In the plasma at the heart of a star, the temperature is so high that the electrons are not bound to any of the protons. They just wander off and become part of the plasma. And most of the mass is left over in the proton, so this is one direction that beta decay can go. You start it with a neutron, and then it splits off and becomes a proton, and then all of the other things go elsewhere. But this process can also happen in reverse, but it doesn't just happen spontaneously. The proton, as far as we know, if left to its own devices, is perfectly stable under normal conditions. Its half-life is as longer than the age of the universe as far as we can tell. But suppose we take two protons and try to force them together. Since they both carry a positive charge, they repel each other. The closer they get, the stronger the repulsive force becomes, and the more energy you have to put into the system to force them closer. Sorry. That's embarrassing. It's a lot like when you're trying to press together two magnets with the same poles. The more you push, the more they push back. And it's very much like that with the protons. So if we can somehow push the protons close enough, then there comes a point where the strong nuclear force suddenly takes over and pulls them the rest of the way together. This critical distance is represented by these two circles. So for this demonstration, let's bring these two together and show what happens. If the protons somehow get within this distance, fusion will happen. One way that this can happen naturally is by colliding two protons together at really high speeds. They have enough kinetic energy to get close enough for the strong force to take over. And in layman's terms, this is if the temperature is high enough, they'll hit hard enough for them to fuse. So the protons have come together, and now the only problem is they don't want to be in this kind of configuration. There's a lot of energy that had to be put into the system in order to force them together. This is a highly unstable isotope of helium called helium-2, and its theoretical half-life is about 10 to the minus 20 seconds. It's very short. And at this point, because there is so much energy bound up in this nucleus, it becomes energetically favorable for a transition to occur. The proton will decay by turning into a neutron, a positron, the positively charged antiparticle of the electron to carry the charge away, and a neutrino, and this is called inverse beta decay. And what we're left with is a stable isotope of hydrogen called deuterium, or hydrogen-2. When I say stable, I mean this will never decay. It is already at its lowest energy state. At this point, let's talk about what happens to that positron that just flew off. So far, we've been focused on the protons and the neutrons, but the electrons are moving around like a gas in the background. In the plasma in the heart of a star, because the temperature is so high, electrons can't bind to any specific proton. So they just keep zipping right on by. When a positron gets near an electron, because they've got opposite charges, they get pulled together. And when they meet, because they're each other's antiparticle, they annihilate and create two photons, which carry away the energy that was once the mass of the two particles. Everybody remember Einstein's E equals mc squared? This is a direct application of that. The mass has turned into energy. The photons that were emitted can be absorbed by other particles, knocking them about, and in general, they just add to the energy of the system of the plasma, which increases the temperature and outward pressure pushing back against gravity. So let's talk about that deuteron that we made earlier. So here's the deuteron right here, this guy. And here is another proton in the system. The neutron holding onto the proton makes it a lot easier for other protons to grab a hold of it and fuse. So the deuteron in this process usually lives for about 1 second before it gets pulled into a reaction to form helium-3. The photon you just saw getting fired off is because the helium-3 nucleus that has formed has just a little bit too much energy for it to be completely stable. So it emits a photon to get rid of some of that energy so it settles down. On average, a helium-3 nucleus will live for about 100 years before it gets pulled into a reaction. And what typically happens is that two helium-3 nuclei will tend to sink to the core of the star, and they'll hang out in the core for a bit until the core's temperature reaches about 10 million degrees. There are now two protons in each of these nuclei, which are pushing the nuclei apart, so the temperature needs to be high enough before they can have enough energy to fuse. But once they do, they come together, and the resultant isotope of beryllium-6 is unstable and almost immediately kicks off two protons to form a stable helium-4 nucleus. And we even gave this nucleus a special name. We call it helium-4, but it's also known as an alpha particle. And the reason why we gave it a special name is because it is so important to other nuclear processes. And I'll show you some of that in just a sec. So So at this point, helium-4 is a stable nucleus. It doesn't really want to do anything but just be left alone. Theoretically, 2 helium-4 nuclei can fuse to become a short-lived beryllium-8 nucleus, but beryllium-8 only wants to be around for 10 to the minus 16 seconds. So before anything new can happen, the amount of helium-4 needs to build up in the core, and it just kind of sits there. This is called helium ash. Meanwhile, gravity is continuing to crush inwards, and the star is using up its hydrogen fuel in order to keep the outward pressure up. Fortunately, this fuel is very, very efficient, and it will usually take a massive star somewhere in the tens of millions of years to get past this point. I say massive star to distinguish it from our sun, which is not really that big. Our sun will go through its hydrogen fueling phase for billions of years. I think the lifetime of our sun is predicted to be around 15 billion, 10 to 15 billion. I don't want to be quoted on that, but it is a very, very long time. So we don't have to worry about this process running out anytime soon. So for each helium-4 nucleus that is made while burning hydrogen, about 6.7 mega electron volts of energy is liberated per nucleon. So I know mega electron volts is sort of this esoteric number, so let me put that into perspective. The amount of energy falling onto the Earth from the sun per second is equal to the amount of energy from burning 3 kilograms of hydrogen to make helium. And that's not per meter, that is the whole Earth. So for every 1 second, the sun has burned about 3 kilograms in order to feed the energy that is falling onto the Earth. Burning 1 kilogram of helium would power about 16,500 US homes for a year, or would be equal the power of about 10 Hiroshima bombs. Nuclear fusion is such an incredible producer of energy that if you were to take only the hydrogen that was in the water in Lake Superior, and you were to burn it in a nuclear furnace like the sun, it would be enough to, it would be the equivalent of the amount of energy that Earth has received in the last 1.5 million years. So helium burning, by comparison, is way less efficient. To begin burning helium, you need the temperature to be about 100 million degrees. And once we have that energy, here's what ideally happens. We first need 2 alpha particles to collide and form beryllium-8. And once we have beryllium-8, the beryllium-8 nucleus, it lasts for about 10 to the minus 16 seconds that it will hold together. It's unstable because the 4 protons are trying to force everything apart, and they're just barely stronger than the neutrons that are holding everything together. In fact, even adding just a single neutron to this configuration would make it stable. And indeed, beryllium-9 is the only stable isotope of beryllium. If this beryllium nucleus is lucky, it will have another alpha particle collide with it in just this brief moment that they're all together. And if this occurs, we have what is an unstable state of carbon-12 called the Hoyle state. And if it is luckier still, it will emit a photon and it will collapse to a ground state of carbon-12. So 2 nuclei come together and they're unstable. A third one comes together, it's still unstable, but it needs to emit a photon and then it can go off as a stable carbon-12. The amount of energy that is liberated from this reaction is about 0.61 mega electron volts, which is about 10 times less efficient than for hydrogen. Helium is also really, really sensitive to temperature. Once its ignition temperature has been reached, if you continue turning up the heat, the nuclear reaction will proceed much faster. It takes about 1 million years for a star of the size of like a massive star to burn through all of its helium reserves before anything new can happen. So that was called the triple alpha process, and the first process that I walked you through is called the proton-proton chain. Those are 2 of the big nuclear fusion kinds of processes, and there's a whole bunch of other ones, but they're kind of messy enough that I don't want to get super far down the rabbit hole. I more or less just wanted to tell you this is how helium is made in the first place, and then how carbon is made, because it is made from from alpha particles coming together. Oxygen would be another such kind of atom that would be made from this. So if in the Hoyle state another alpha particle hit it, it would wind up creating oxygen. So now that we've discussed how alpha particles create the proton-proton chain and we've looked at how carbon is formed, let's zoom back out and take a look at the full life cycle of a massive main sequence star from birth all the way up to death. We start with a nebula, which is just a sparse cloud of gas loosely bound by gravity. And as gravity starts to take hold, the sparse cloud begins to collect together toward the gravitational barycenter. So there's a spot of increasing density in the middle. When the temperature at the center reaches about 1,000,000 degrees, deuterium starts to fuse. This is the primary nuclear process in very low mass stars called brown dwarfs and some very large planets. This starts a small ignition in the interior region and slowly burns outward as deuterium fuel is used up. This process actually slows the inward contraction of dust for some short amount of time, about 100,000 years to 1,000,000 years. When the deuterium fuel is used up, the cloud will continue its gravitational collapse. And as the dust collapses, it will eventually get to a density where there starts to be pushback on the infalling cloud. And a very thin surface will begin to form. And this region distinguishes the protostar from the nebula that is accreting into it. When enough material has fallen into the star that the temperature at the very center reaches 10,000,000 degrees, we begin to start seeing the start of the hydrogen burning phase. This is a really slow process. The reason why it's such a slow process is because it takes about 10 to the 30 collisions to successfully produce one deuteron. Once a deuteron is created, it almost immediately grabs another proton, roughly after about 1 second, and then it forms helium-3 in a helium-3 nucleus. And then that helium-3 nucleus bounces around for a few centuries and before it finds another one, and then they lock together and become helium, or helium-4. And the reason why this astronomically unlikely event occurs at a frequency enough to literally hold up the surface of a star is because there are so many of these collisions taking place. So for example, our sun produces something like 3.8 times 10 to the 26 watts of power. A back into the napkin calculation equates this to about 10 to the 38, or in other words, 100 billion deuteron formations every second. So this implies that there's 10 to the 68 collisions happening every single second. So that sort of gives you some idea. And our sun is a relatively small star, so this is not representative of all of the stars out there, just our sun as just an example. So eventually, the helium ash begins to build up in the core of the star, and it just sits there doing nothing for a long time. At about 100,000,000 years, the helium begins to burn, and we start to see, at 100,000,000 degrees, the helium begins to burn. We start seeing the unstable beryllium-8 nuclei occurring often enough that a third alpha particle finds its way into the collision and they all stick together. And of those Hoyle states for carbon, about 1 in 16 to 1 in 2,500 actually emit the photon and survive. All of the other ones, they just break back apart and continue on in the plasma. It is during the helium burning phase that oxygen is also created as a carbon nucleus, fusing with another alpha particle. The next burning phases get messier, so let's just simplify and say qualitatively that when carbon and oxygen levels get rich enough and the temperature gets high enough that these also will start to burn. But we're getting to the end of the star's life cycle. The fusion of these larger nuclei does add to the system, but not anywhere near as much as the hydrogen does. As the larger nuclei form, more and more energy is carried away in the form of neutrinos, and less of it is thermal energy that is holding up the surface of the star. So gravity is starting to win in this battle of attrition. With each new layer with each new fusion layer it burns through, the fuel is burned faster and faster. It takes about 1,000,000 years to get through all of the helium, and it takes about 1,000 years to get through all the carbon, about a year to get through all of the oxygen, and a few days to get through all of the silicon. It's at this point that the death knell for the star starts to ring, because at this point iron ash starts to build up in the core. Once we get to iron, it is a poison pill. It actually takes energy to fuse more nuclei onto an iron nucleus. So to create larger nuclei, it would pull energy out of the system. The only thing holding up the star when the iron core starts to fuse is actually the electrons flying about. Once the mass of the iron's core reaches about 1.44 times the mass of our sun, though, the electrons can't hold it up anymore, and the core suddenly collapses. Because the electrons are already moving very close to the speed of light, they can't go any faster. So rather than try, it becomes energetically favorable for electron to be captured by a neutron or be captured by a proton and become a neutron. So that's exactly what happens. And then the core, which was about the size of the Earth, then suddenly collapses into something about the size of Manhattan. All in the span of about 1 second. A super hot core of about 90% neutrons and about 10% protons is then formed. I could give an entire talk about the neutron star itself, and perhaps we will get to do that at some other future talk, but for now, let's get back to the action. At this point, the rest of the star collapses upon the newly formed proto-neutron star, and if the star is massive enough, it can compress the neutron star yet further and collapse it into a black hole. If it's not quite that massive, then the neutron star will be a rigid body in the center, and it acts kind of like water hammer. So all of a sudden, the cavitation that was left behind gets filled by the infalling matter, and it sends a shock wave that will propagate through the rest of the star. In either case, the shock wave will accelerate it as it passes through the layers, going through silicon, neon, oxygen, carbon, helium, and it tears the star apart as it passes through. This is how heavier elements from the inner layers of massive stars get blown out to eventually find their way into our solar system. This is a picture of Cassiopeia A, which was taken from the Chandra satellite on December 12th of 2017. This is actually a composite image created from looking at the same event in multiple different wavelengths of light. So for example, this is the silicon that we can see from this event. It's the spectral lines that only come from silicon. This is sulfur. This is calcium. This is iron. And this is the blast wave of high energy X-rays. This allows us to map the expanding blast wave around the actual event. This is what you would see if you were looking at it through a telescope. This is the visible spectrum, so we wouldn't see much of anything. But by layering different spectra on top of each other, we get a pretty good composite view of the actual event that happened. You can even see the neutron star in the very center of the blast, right there. At this point, you may be thinking to yourself, well, this is really cool, but why did we just spend 20 minutes talking about nuclear physics? Psalm 8:3 through 4 says, "When I consider your heavens and the work of your fingers, the moon and the stars, which you have set in place, what is mankind that you are mindful of them, human beings that you care for them?" I wanted to take some time to walk through what typically happens in our universe so that heavier elements like what the Earth is made of can be made. Most of the elements in our universe, about 75% of it is hydrogen. About 25% of it is helium, and anything heavier than that only makes up very trace amounts. I mentioned during my last lecture the idea of the anthropic principle, which is the observation that fundamental laws and constants of our universe appear to be precisely calibrated to allow for the existence of complex structures, including stars, planets, and not just life, but intelligent life. If you dig into the anthropic principle at all, you'll discover a rather long list of stunning Goldilocks examples in many different fields. So from cosmology, we have the cosmological constant that determines how fast the universe is expanding. From mathematics, we have the dimensionality of space. From astronomy, we have the Earth is in a very precise region in our solar system that allows for liquid water. Our sun is also just the right size to burn for billions of years. In chemistry, water expands when it's frozen. It has a high heat capacity and is an incredible solvent. And this list is not at all exhaustive. I mentioned during my last lecture the idea that, hold on, keep going, there we go. I'm going to pick up just a few of these, which are relevant to what we've already discussed so far to dig into. But as you just saw, there's already enough topics to fill a year's worth of presentations. So before I proceed, I'd like to clear something up. Before we talk about constants like the speed of light or the Planck constant, the value of these constants depend on what units we use. So I could theoretically talk about the speed of light in furlongs per fortnight, but that's not particularly helpful. However, there are combinations of these constants that we can pull together and make unitless constants that don't depend on what units we use. And in fact, as far as we can tell, these constants are as fundamental to this universe as the value of pi or the constant e, because they don't depend on our frame of reference. They just are. Back up. One of the fun things about physics is that we get to ask, what if, and follow the logic from some basic assumptions to see what happens. When scientists measure the fundamental settings of the universe, things like the strength of gravity, the electromagnetic force, the masses of basic particles, they discovered something remarkable, that these values all fall within extremely narrow ranges that make our universe habitable. If any of these constants were even slightly different, it has catastrophic effects. So for example, let's talk about the fine structure constant for a moment. This constant is essentially nature's dial on the electromagnetic force. It determines how strongly electrically charged particles interact with each other. It's a unitless constant whose approximate value is 1 over 137. And it's here is the definition with a number of other physical constants. So E is the unit charge. It is the charge of a single electron. We also see epsilon naught, which is the electric permittivity of the vacuum. H bar is the Planck constant, which is a measure of how quantum the universe acts. And C is the speed of light, which determines like how fast information can travel across the universe. We can represent all of these constants in different ways, depending on what units we choose to use, but alpha seems to be a fundamental constant of the universe. It doesn't change regardless of what units we use. We actually see the fine structure constant in a lot of places, but let me tell you what happens if we start changing it. Let's start by turning it up higher. In the early universe, just after the Big Bang, there was a brief window where some of the protons fused into deuterium, into helium-3, helium-4, and trace amounts of lithium and beryllium. If alpha were bigger, less helium would have formed because the protons are more strongly repulsed by each other. This would have affected the distribution of elements in the early universe. In stars, the temperatures would have to be higher, which would mean that stars would tend to be more massive to begin nuclear fusion. They would, in general, burn more slowly because it takes time for their cores to get hot enough to fuse efficiently. And this also means that shorter-lived stars and heavier elements would become harder to create. If you increased it too much, there wouldn't be stars burning at all. For chemistry, this would make atoms themselves smaller because the electrons would be more strongly attracted to the nuclei. The heavier stable elements would become unstable because the electrons around heavy elements would have begun moving at relativistic speeds faster, which is actually something that happens with really heavy nuclei. So if the electromagnetic force were stronger, then this would happen for smaller elements. Chemistry would be completely different because electron orbitals they dictate how molecular bonds happen. Creating molecules would change because you would need more energy to make and break chemical bonds. Hydrogen bonding and van der Waals forces would change, such as phases and solvent properties of water can move outside of life-friendly windows. So the universe in general would tend to be filled with lighter elements that would tend to have simpler chemistry. The complex chemical reactions needed for life might not ever be possible in such a universe. If we turn alpha down, in this scenario, the early universe would have a different mix of hydrogen and helium and light elements. When stars start to form, the electromagnetic force repelling the protons would be lower, so fusion would start at lower temperatures. Smaller objects like brown dwarfs or even planets the size of Jupiter could sustain a fusion reaction. Most stars would tend to burn hotter and faster and would tend to have shorter lifetimes. In the course of these stars, heavier nuclei would be relatively more stable against the Coulomb repulsion. So there would be relatively larger nuclei, and this would also change reaction rates, and it would change the distribution of carbon and oxygen. For chemistry, this would make puffier atoms with weaker bonds. Ionization and bond energies would drop. Molecules would be easier to make, but they would also be easier to tear apart. Too much heat or even too bright of a light shining on it could destroy a molecule. This already happens with, like what you were saying with the sun. It breaks down chemical bonds in plastics. This would be yet easier with more molecules. It would also destroy or lower melting and boiling points, potentially turning solid rock into magma at lower temperatures. Our universe, and in particular life itself, seems to demand a very specific range for alpha, small enough that fusion can happen, and gentle enough to allow for long-lived, stable stars, but large enough for chemistry to be structured, and selective, but not so large that heavy elements are impossible. Oop, I think I went back. There we go. So this is alpha sub g. It's the equivalent cosmic gravitational volume knob for the gravitational force. This wouldn't have many effects on chemistry itself, other than monkeying with the stars that produce the elements. But if the force of gravity were stronger, stars would collapse to higher densities faster. They'd ignite at smaller sizes. They'd burn fuel more quickly, and short-lived massive stars would dominate our universe. Stellar lifetimes would tend to be too short for planetary systems like ours to develop and remain stable enough for millions of years for the complex chemical processes necessary for life to begin. Also, frequent supernovae would make galaxies more violent and less hospitable for life in general. If the force of gravity were weaker, it would be harder for stars to reach fusion temperatures, and many nebulae would never ignite at all. Only supermassive stars would ever shine, and dinky stars like our sun would never exist. The night sky would have much fewer stars and much dimmer galaxies. Another interesting constant, at least to me, is the ratio of the masses of the proton and the neutron. The difference between these two masses is small. It's about 0.14%, yet that is absolutely crucial. So for now, let's leave the mass of the proton fixed. If the neutron were just a tiny bit lighter, 0.05% would be enough to make it stable, and it would never decay. The proton-proton chain that we talked about in the very first part of the lecture would become even more exothermic, which means easier fusion. The universe would end up with almost no hydrogen. Most of the hydrogen produced in the Big Bang would fuse into helium almost immediately, and this would by itself make it nearly impossible for water to form. And long-lived hydrogen in burning stars like our sun would become scarce, if not existent. Basically, all of the fuel in the universe would be burned up in the first few moments, and then nothing would be had for later. If neutrons were just a little bit heavier, by about 0.18%, they'd decay faster. That would leave less helium and more hydrogen in the early universe, but more critically, the first step of fusion is turning two protons into a deuteron, and that would become endothermic. In other words, it would cost energy rather than release it. And even bringing two protons close enough together wouldn't be enough to flip one into a neutron. Without that spark, stars like our sun would never ignite, so the universe would be filled with what is supposed to be fuel, but it just won't burn. The ratio of the masses of the proton to neutron is so perfect, it is absolutely baffling. So after spending the last several weeks immersed in the research for this talk, I have been struck again and again by what a miracle it is that we are able to look up at the night sky and ponder God's beautiful, delicate, awesome creation. In Isaac Newton's Principia, he wrote, "This most beautiful system of the sun, planets, and comets can only proceed from the counsel and dominion of an intelligent, powerful being. This being governs all things not as the soul of the world, but as Lord over all. And on account of his dominion, he is wont to be called Lord God." So we stand here, we're made from the dust from ancient stars, had life breathed into us, and given minds to ask questions and eyes to see the heavens. The same God who sets the constants and kindled the stars has written himself into our story. My hope is that the next time you look up at the night sky, you don't just see points of light, but you see an invitation to wonder and to worship. So, are there any questions? Yes, sir.
We've talked about years and years, billions of years, just a lot of time transpiring just from, a star forms pretty quick, apparently, because everything burns up real quick. But my question is, how far into the billion years of the life of the sun are we? And is the beginning of the life cycle factored into the cycle where it's going to end its end phase in billions of years?
Okay. If I remember right, we are about halfway through the sun's lifetime. I think, if I remember right, the Sol has a predicted lifetime of about 10 to 15 billion years. and we're about 5 billion years into that. So a third to half, depending on like which model you use or which number you believe. But in either case, we're like somewhere in the mid range of it. Did you have another question? I'm sorry.
No, I just wanted to make a comment. Computer, plot the course to the nearest planet to get a beryllium sphere. That's a movie quote, but we were talking about beryllium, so if you know the quote, yeah.
Talking about
Galaxy Quest, yeah.
Love it.
It's a spoof on sci-fi.
Thank
Yeah.
you so much for nerding that out. I love that you said that. I love Galaxy Quest. That's awesome.
Yeah, so they use a beryllium sphere to power their spacecraft. And it's compromised, they have to find a beryllium sphere.
You all need to watch the movie now. It's
Do
great.
you meet other scientists who are willing to discuss or struggle with the idea that there does appear this exquisite design? Does that
So-
conversation come up at all?
Actually, yes. That was one of. So I did my grad work at Texas A&M, and there were students who were scientists and Christians. There were also students that were scientists and atheists, and like we would sort of have high-level conversations about this stuff. And the general consensus among all of the Christian scientists that I knew was, how do you see this and not see God in it? And the general feeling is that if you know God, you see Him everywhere. If you don't know Him, you just don't see it.
You can't.
And like there's all sorts of different kinds of differing philosophies on that kind of thing. I look at this kind of stuff and I see His fingerprints all over it. But I also grew up with this, and I have been studying this for a long time. I cannot remember a time in my life that I didn't know God was behind all of the scenes. So for me, this all makes perfect sense. So I hope that answered your question.
So Alex, in kind of talking about our galaxy, talking about the sun and everything, it's a fairly stable unit.
Yeah.
And so, you move a planet inward or outward, or you move the sun closer to one of the other planets, and the whole galaxy becomes unstable. Is that true?
No. So the like what we were talking about with global warming, like if you threw the whole of the Earth into the sun, the sun's not going to do a whole lot different. The same thing is kind of true for the rest of the galaxy. Like if something happens in our solar system, it's not going to affect other stars that much. So it's a matter of scale. The Earth is like 1/1,000,000th the size of the sun, so throwing a little marble into the sun isn't going to change that much. And likewise, our sun is not very small compared to the whole galaxy.
But is it a kind of a chicken or an egg type of thing? I mean, did the sun create the galaxy, or the galaxy create the sun? That type of thing.
The galaxy created the sun. It was the galaxy started as just like a big collection of matter in the early universe, and that collection kind of fell into the galaxy that we know. The stars, there were a bunch of nebulae that formed a whole bunch of stars, and the stars, like when they explode, they cause shock waves that go through the nebulae, which also like propagates through and cause more collapse of other stars. So like it is, the galaxy came first, and then our sun, and then our planet.
Because we're on the edge of the galaxy pretty much. Like,
We're actually
one of the arms.
We're actually in between two arms. I think it's the Sagittarius and the Perseus arms. I don't think I remember those names exactly correctly, so don't quote me on that. But yes, we are in between two of them. And actually, that is another thing for the anthropic principle, is the fact that we have the ability to see out into the night sky. If we were inside of one of the arms, it would be a lot harder for us to see through the dust and gas. We wouldn't know how big the universe was.
Are more planets being made?
Yes, all the time.
More what?
Not in our solar system, I should mention, but like all over the galaxy, all over the universe. Yes, there's constantly new stars being born, and in that process, more planets are being made. Yes, sir?
So would you equate the material that makes the galaxy, God created the materials that created because you're saying the galaxy created the sun and so on and so forth.
So the galaxy was basically just some section of the whole universe that just had a bunch of hydrogen and helium and stuff that eventually collapsed into itself and turned into what is now our galaxy. So, like, there's other galaxies that are sort of orbiting our galaxy right now that are sort of in the process of falling into our galaxy over the next 100 billion years or something.
Maybe God created the helium and such that formed everything in the galaxy.
Yeah. Yes, sir?
Yeah, she mentioned something about solar systems that make planets being made.
Uh-huh.
And I wonder, do most solar systems have around 8 to 10 planets, or can it like vary?
That varies a lot. Actually, if you look at all of the stars that are out there, every one of them has a certain distance at which liquid water would exist. Our sun is really nice in that it is a relatively small star with a relatively stable life cycle. That, like you were talking about solar flares and such. If we were around a red dwarf, for instance, that would be a lot worse because there would be more solar flares happening all the time. It's less hospitable. Another thing about red dwarfs is that the habitable zone is much thinner, so it would be less likely for a planet to form in that zone. Our sun is large enough that we have a wide enough band that we're actually doing pretty good to have a planet in that habitable zone for long enough for us to be here. But even very large stars also have a similar distance that would have that same range of where water would exist. Does that answer your question?
Good question.
Yes, ma'am?
How common is it for there to be a single star and to not have two stars? Because so often it's
Actually, it's really uncommon. Most stars that we know of tend to be in binary or ternary systems. The fact that our sun is alone is sort of unusual, and it likely happened earlier on. Our sun was probably part of a ternary system, and at some point, our sun was the one that got kicked out. But there are all sorts of really chaotic kinds of systems out there, one of which I know has 7 stars all orbiting around in some sort of stable orbit. It's incredible. But yeah, that is not at all uncommon for binary systems, and actually that is typically the norm. Our sun being by itself is a little unusual. There you go.
So you're saying the 3-body problem could actually happen?
The 3-body problem happens all the time. Actually, one of the reasons why that is such a weird problem is because with two bodies, all of the orbits and whatever are perfectly 100% stable. So a 2-body system will orbit itself relatively normally forever after that point. But a 3-body problem, as soon as you start adding a 3rd body into it that is massive enough to change the orbits of the other 2, it becomes chaotic. And what I mean by that is very small changes in the early initial conditions will change radically how it affects later on. So the 3-body problem, like what you see on the show for Netflix, that is actually like a problem that would happen with a planet that would be in a ternary system. The stars would go for millions of years or even thousands of years or thousands or millions of years in a stable orbit, but as soon as the 3rd body comes in, it will affect the gravitational pulls and throw things into chaos, and then it will sort of settle back down for a little bit, and then it will go back into chaos. It goes back and forth.
2 questions. First one, if you have a binary sun, it would seem like you don't have day and night on planets. Yes or no? Or
So there's actually a number of different configurations for how a binary system would work. So to give one example, if you have a sun right here and another sun right here, you could have a planet orbiting one of those stars. But another stable configuration would actually be something more like Tatooine, where you have a planet that is orbiting around both of these stars in the center. So like they're right here, and the distance to the planet would be much further out. You would see 2 stars in the night sky. If you're orbiting all around one of them, then it is actually not really habitable for life. You would have to be close enough to the star that you would have too much light hitting that planet too often for water to really exist. So this is really the only stable configuration that would make sense. The only problem is that in order for the habitable zone to work, you'd have to go further out.
Way out. And the follow-on to this is how in the world does this relate to Lockheed?
I'm good at pushing numbers around a whiteboard, and that's what they hired me for.
So they don't pay you to know all this other stuff.
So you'd be shocked at how often I wind up using some of this esoteric knowledge in Lockheed. Like I once solved a problem in radar that using a solution that was inspired from general relativity. Most of my peers probably wouldn't have the mathematical fortitude to do it, but I just saw a connection there and I was able to put it together. So like, I think that's one of the reasons why they hired me in the first place, was because I think differently than most of the people around me.
That's obvious.
Yeah. Yes, sir?
So, do you think that people or any kind of animal would be able to possibly move to Mars, or do you think that is simply captivating science?
So actually Mars is, like if you find some way to get enough atmosphere there, like oxygen for them to breathe, it's actually really habitable. You would need to have some way to protect them from the solar radiation because Mars's magnetic field is not very large. So there's more radiation coming through that would actually hit them. But if you could protect them from that, if you could give them enough oxygen, it's actually more habitable than you'd think. But all of that stuff would have to come from Earth.
I'm reading a sci-fi book with the little goggles and hats. When they're outside.
Oh yeah?
They need oxygen too.
They do.
The author covers all of those things in the book.
Anybody else?
No.
No? Cool.
All right, thank you, Alex.
Appreciate it. Thank you. Oh, yeah.
All right, so just a brief moment here to close. Yes, these seminars are not equipment intensive at all. Now, in closing, I always say this, but I say it again. I'm so appreciative. Bob and I are both so appreciative that you're here. It just makes all the difference in the world. Again, I would ask that you spread the word to other people. You've got the October flyer. There's already flyers for October posted in the in the fellowship hall. So please spread the word. I was praying for 40 today, but God has His own timing, and all I can do is continue to pray and hope. So thank you again for coming. One thing, we don't have the slides up anymore, but one thing I would like to hope that all of us see is what we talk about a lot here is science, but also when we look at these pictures of nebula and the sun and the math and all that, there is an absolute beauty to that, like artwork. This is both art and science. And the art part's a little bit harder to see sometimes. So I just encourage you to, when you see some of these slides in the future and in the papers that you've been given, that you kind of look at it with an artful eye too, at how magnificent and how beautiful our God is. All right, so again, thank the speakers here, Glenn and Alex. Thank you. And so,
Thank God for them too. Thank God that.
oh, thank God for them. Thank God for everything. And like Glenn said, his shirt actually has a lot of beauty in it. If you can just see past the math and the symbols. Yes. All right. Now, just something to point out. We've had 7 speakers now to this point. By the end of the year, we'll have had 10 speakers. Several of them have made multiple presentations. They're all from within our church. We are a blessed church.
Amen.
We are.
So, if you would like to make a presentation and or know someone you think might make a presentation, not everybody look down, please let me know, because we always are looking for new people to speak. Certainly, these dedicated men will be back to speak again, but we always need new people. And we're looking at other speakers, too, outside the church that might come in next year. And in fact, we already are scheduled into January and February of next year, at least 50% of that right now. So next month, it's going to be Glenn, again, talking about the sun and how it affects the human body, which I am a living example of how it's affected the human body. I'm one of the few people on earth that does not tan, and I have plenty of craters up here to prove that the sun does affect me. Anyway, and then Cody Bailey will be here to talk about God's glory revealed in electromagnetism. So, Bob, could I ask you to come forward?
Want to say something?
I want you to close us in prayer, my friend. And by the way, if without the inspiration in Bob from the Holy Spirit and God above, we wouldn't have this seminar. He may sit over there, but he's actively involved in everything we do. And I couldn't thank him enough for letting me have the opportunity, the humble, gracious opportunity to help him in this endeavor. So I want to give Bob some thanks too, please. If you would just say something and then close us in prayer.
I'm a chemical engineer, so I deal with creating, I design reactors, chemical reactors, and reaction design to promote products. But we generally focus on making a product. We have all these side reactions we try to minimize. But what we're going on here, we're talking about today, the formation of carbon and nitrogen and oxygen are kind of, they just occurred, but they're not the main, they just occurred. But the fact that all these things occurred the way they did, the improbability of them just, of life coming together on its own is just so improbable. The fact that God orchestrated the creation of life using these elements, and he did it. He caused it to happen, and we're here because of that. But I'm going home today with my mouth closed in awe of the great grandeur of God and what He's done. So just think about Psalm 8. When I consider your heavens, the work of your fingers, the moon and the stars which you have ordained. What is man that you take thought of him, the Son of Man that you consider him? It's a beautiful thing to know that we are here because God created life. The improbability of that happening is just amazing, but the fact it happened, and we are here. It's God has spoken and created life, and we praise Him for that. So let's do that. Let's praise Him now. Father, thank you for granting us, creating our lives, but even more than that, thank you for giving us life in Jesus, the Son, who we might enjoy you forever in all that you have done, Lord, through creation and in redemption. We ask, Lord, that you would cause us to grow in our love for you and our attraction for you, that our affections of our hearts would be increasingly devoted to you. Lord, thank you for bringing us to life and allowing us to enjoy how you created all these things for your glory. And so, Lord, in your name we pray. Amen.
Amen.